Right? Section 8.5, Dalton's law of partial pressures. Dalton's law of partial pressure says that for a mixture of gases in a container, the total pressure is going to be the sum of the pressures that each gas would exert if it were alone. So remember, gases are mostly empty space. We get the pressure from when an individual gas molecule collides with the container wall or with the surface. And so if I've got another gas in there, it's going to act, and its particles are going to impact that container wall or that area at simultaneous with all the other ones, but independent in operation. So our gases are going to sum up their pressures to give an overall pressure, and that total pressure is just the sum of the individual pressures of a gas. So P1, P2, P3, and so on each represent what we call a partial pressure of those individual gases. Partial pressures of each gas can be individually calculated when it is assumed each gas behaves ideally. So we've got P1 is equal to N1 times RT over V, P2 is equal to N2 times RT over V, P3 is equal to N3 over RT over V. Now, when we're doing this, right, it should become pretty easy, right, to make some stuff drop out. So if they're in the same container, volume is always going to be the same. That's why we don't have a V1, V2, V3. If they're in the same container, the temperature is going to be the same. That's why we don't have T1, T2, T3. Right? So you can see that this total pressure is really going to be proportional to the moles of each of these things. Right? It's a little hint. So here's our gas. We got one blue gas, right? And then we got a red gas. And if we're looking at the number of impacts on this container, right, the pressure is going to be the sum of all of those, of both of those, right? So our total pressure is going to be the sum of the individual pressures. Right? Our partial pressure is the pressure that one component of a mixture of gases would exert if they were the only one in the container. Right? So if I've got one gas by itself and it's got a pressure of 1, 2, 3, 4, right? And I mix it with another one that's got and I measure them both together, and that comes out as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This guy's 4, and this guy's 10. I can figure out that the partial pressure of this red one is going to be equal to 6. Right? So if we've got a total pressure, that's going to be the sum of the pressures from nitrogen and the partial pressure from oxygen. And so if I look at this, the total pressure exerted by the mixture of gases in a container at constant volume and temperature is equal to the sum of the individual gases. Right? So our total pressure is P1 plus P2 all the way up to P infinity, and this is assuming that these gases do not react, right? That they're not going to interact with each other. And the exact formulation is the pressure exerted by a mixture of gases equals the sum of the partial pressures of the gases in the mixture. Right? Because our pressure and our volume are constant. Because the temperature and the volume are constant. Our pressures are going to work as stand-ins for moles. And what we can compute is this thing called a mole fraction. And a mole fraction just says, what's the moles of one species, one molecule, over the total number of molecules in the mixture. So we've got X sub I is going to be equal to Ni over N total, right? Which is going to be the same thing as saying that our mole fraction is going to be equal to the pressure of an individual component divided by the total pressure. One of the ways that we can obtain gases is by collecting gas over water. This used to be a very common experiment to do in Gen Chem. I will, if you have me in one of my upper level classes, we will probably do this just for fun so that you guys can get experience, but it's pretty simple to do and you can actually do this pretty easily. So gaseous mixtures are a result of gas collection due to displacement of water. When the rate of escape of vapor is equal to the rate of return, the number of water molecules is going to remain constant, and the water pressure is going to remain constant. This pressure, dependent on temperature, is called the vapor pressure of water. So here we've got our gas generating apparatus. So we got some potassium chlorate and some manganese oxide, and we're going to heat it up. And this is one of those oxygen gas generating reaction. So oxygen will be generated. Right? We'll get O2 gas, O2. Right? That O2 gas doesn't have anywhere to go except down through this glass tubing. Right? And keep going through the glass tubing. And then it'll bubble up into this container. And as it does so, these oxygen bubbles are going to push, that gas is going to push that water out. Right? The water level will actually go up a little bit. Right? And we're going to collect the oxygen gas in here. Right, so let's look at an example of what we can do with this. A sample of solid potassium chlorate is heated in a test tube and decomposed by the following reaction. We've got potassium chlorate plus heat, right, is going to give us 2 potassium chlorides and 3 oxygen gases. The oxygen produced was collected by the displacement of water at 22 degrees C and a total pressure of 754 torr. The volume of the gas collected was 0.650 liters, and the vapor pressure of water at 22 degrees C is 21 torr. Right, so in our little container here, we've got 2 gases, right? We put in some O2, but also we've got some water vapor that is able to escape and get up in there, right? Because our water is going to evaporate a little bit. And so at a given temperature, you will always know how much of that water is trying to vaporize. That's your vapor pressure. That's another way to think of that vapor pressure of water. Right, so at 22 degrees C, the vapor pressure of water is going to be 21 torr. So part of that total pressure is coming from water. Part of that total pressure is coming from oxygen. We want to calculate the partial pressure of O2 in the gas collected and the mass of potassium chlorate that was decomposed. Right. Looking at the information available in our collected gas, we know the pressure was 754 torr. The volume was 0.65 liters, and our temperature, we converted into Kelvin, 298. The temperature is the same for the water vapor, and the vapor pressure, we were told, was 21 torr. Right, the volume will be the same. It's going to be the same volume in there. So calculate the partial pressure of O2. The total pressure, 554 torr, is going to be the sum of the oxygen and the water. So it's going to be the partial pressure of oxygen plus 21 torr is equal to 575. So we do 754 minus 21 torr is equal to 733 torr. And that's our partial pressure of oxygen. Right? From there, once we've got the pressure, we got the volume, we got the temperature, we can calculate the number of moles of oxygen. So the number of moles of oxygen are going to be equal to the partial pressure of oxygen, so just the oxygen one, times the volume divided by R and T. So we'll do 733 torr. Right? We're going to convert that into atmospheres, right? Because R is in liters times atmospheres per mole Kelvin. Right, we got 0.964 atmospheres. To find the moles produced, we're going to use our volume, our temperature in Kelvin, and our pressure in atmospheres, and the ideal gas constant in liters atmospheres moles Kelvin. So rearrange to find N. So N is equal to PV over RT. So we've got our pressure, 0.946 atmospheres, our volume, 0.65 liters, R, 0.08206, and our temperature, 295. And we get 2.5 times 10 to the minus 2 moles, so 0.00259 moles. Okay. Now that we've got the number of moles, now we can do our stoichiometry. So we're going to balance our chemical equation. So it's 2 KClO3s gives me 2 KCl's and 3 O2s. We're going to calculate the mole ratio between the potassium chlorate and the oxygen. It was a 2 to 3 stoichiometry. We know that we've got 2.59 times 10 to the minus 2 moles of oxygen. We'll use our 2 to 3 stoichiometry. And we get 1.7 times 10 to the minus 2 moles of potassium chlorate. To calculate the mass, all we do is we take our moles of potassium chlorate, multiply by the molecular mass, 122.6 grams of potassium chlorate per 1 mole of potassium chlorate, and we get 2.12 grams of potassium chlorate. Thus, the original sample had 2.12 grams of potassium chlorate.